Hello everyone. In this video I'm going to go over the homework on the one mean z-interval procedure, otherwise known as confidence intervals for normal distribution. So here at the top I have this beautiful gold box that I made, and it's gold because this is a very valuable and important procedure. So we have the variables, here's what they stand for. These are the things that are going to be down here in the formulas, unless they're actually explained down here somewhere else like alpha. And then these three assumptions here, this is something we have to check is true before we can actually use this procedure. The interpretation down here will not be valid unless these assumptions are all true. Now, the third one is a little bit squishy. Sometimes there can be something in between the data being normally distributed and the sample size being large. There's like a medium assumption that you can check, but I wanted to keep this fairly compact. And then you have your steps here, so as long as you follow these steps and then fill in your interpretation sentence, this will work, even if you don't fully understand why it works. All right, so let's go ahead and answer some questions using this procedure. So each problem is more or less divided into three parts. Check the assumptions, follow the procedure, like the middle 5 steps here, and then make an interpretation of the meaning, which is this last little part here. All right, so a company that manufactures coffee for use in commercial machines monitors the caffeine content in its coffee. The company selects 50 samples of coffee every hour from its production line and determines the caffeine content. From historical data, the caffeine content in milligrams mg is known to have a normal distribution with standard deviation 7.1. During a 1-hour time period, the 50 samples yielded a sample mean caffeine content of 110 milligrams. Okay, so presumably what we want to do here is come up with a confidence interval for the population mean for the whole production line, not just these 50 samples. So we're going to use the procedure to do that, but first we need to check that the three assumptions are met. So the first assumption was the sample selected randomly? Okay, so random sample. Is that in here? Let's see. You know what? It does not say random. It says the company selects 50 samples of coffee every hour from its production line, but it doesn't say that it's done randomly. So in this case, what should we do? Unless I've instructed you guys to just like stop and don't proceed if the assumptions are not met, I think what I would do is proceed with some caution, and I would include in the explanation at the end that the conclusion is only going to be valid if this actually was a random sample. I mean, most companies, I assume, would be smart enough to do a random sample, but you never know. I mean, they might grab just like the last box that comes off the line and take 50 in a row instead of 50 random ones. So, not sure. Let's mention this in the interpretation. Okay, so assumption B, the population standard deviation sigma is known. This is the most shady assumption for this procedure, and it's why the procedure is not actually used that much. Because why would you know the population standard deviation if you don't know the population mean? Finding the population standard deviation is just as hard as finding the population mean. So it's kind of a silly assumption. But we start with this procedure anyway as a place to learn from, and then we can move to more challenging procedures as time goes on. Okay, so anyway, from this problem, it is said that from historical data, we know the standard deviation is 7.1. So we're going to go with that assumption. The problem says sigma is 7.1. Oops. All right, and then the last assumption is about whether the sample means are really going to be normally distributed or not. So in order for the sample means to be normally distributed, either the original data needs to be normally distributed, or the sample size needs to be large, or something kind of in between. You can have like a medium sample size of, say, 10 to 20, as long as the data is not too abnormal. We'll talk about that in a future problem. But for this particular problem, it's a sample size of 50, so that is considered large. This sample size is large, 50. Okay, so we verified or made a note of the three assumptions. We're going to mention this one again in the interpretation. Now let's go ahead and do the math part. So for step 1 here, calculate alpha. So alpha is 1 minus the decimal form of the confidence level, and this is the area that is going to be in the tails of the distribution for the sample means. But you don't have to know that to calculate it, just follow this formula here. So alpha is going to be 1 minus, and what is our confidence level? So, oh, right, down here it says 95% confidence interval. So that 95%, that is the confidence level. And we're going to subtract the decimal form. I mean, I hope it would be obvious since you're subtracting it from 1 that it should be the decimal form, but I just made sure to say that it's the decimal form anyway. So 1 minus 0.95 is going to be 0.05. All right, so that's our alpha. That's the total tail area. And then we have to split that into 2 because half of that's going to go in the left tail and half is going to go in the right tail. So anyway, alpha over 2, 0.05 over 2. If you need a calculator, you can use it at this point. I believe this should be 2.5%, so 0.025. Now you need to look up what is z sub 0.025. So you'll either be given a list of z alpha values to refer to, or you might have to do a reverse lookup in the normal distribution table. So let me show you how to do that. Okay, so the most important thing to remember is that when I put the little subscript on z like this, that means I want the z that has that area to its right. So this is z with 0.025 area to its right. If you accidentally look up the z with 0.025 area to its left, it's the right z, but it will be negative and you want the positive one. So you can actually do it like that. Let's just go ahead and do it like that. So I'm looking in this part of the table for reverse lookup. I'm looking for 0.025 in here. So 0.02, oh, this is pretty, oh, right there. This might be the only one that actually appears in the table and it's not between 2. So negative 1.9, z is negative 1.96. But remember, this is the one that has that area to its left. So using the fact that the normal curve is symmetrical from left to right, the z that has that area to its right will be positive 1.96. Okay, so this is going to be 1.96. And let me just show you. So if I look up 1.96 on this side of the table, it's 1.90123456. That z-score has 0.9750 area to its left, so that leaves 0.025 area to its right. So that's the one that is symmetrically placed from negative 1.96. Okay, anyway, somehow you get the z-score. It always comes out to be a positive z-score. Although, you know, even if it didn't, I think you could still do this part. You would just get a negative number here for the margin of error, and then you'd be subtracting a negative here and then adding a negative here. So like you would still get the 2 endpoints of the confidence interval. You would just have them reversed, but presumably at that point you would figure out that the smaller one was the left and the larger one was the right. So I don't even think it's a big deal to mix up the positive and negative here. Okay, anyway, somehow you get the z-value. And now for step 4, we're doing the margin of error. This is the formula. So E stands for margin of error. Okay, I'm just going to paste this formula down here. Okay, so my z-value was 1.96, and I'm multiplying that by sigma, which was up here, it says 7.1. Okay, oh, I'm getting in the right spot, 7.1. Okay, and then on the bottom, I'm doing square root of the sample size. The sample size was 50. Okay, so now I'm putting this all into a calculator. If you're using a for function, you need to be really careful with this step here. I guess I would do the square root of 50 first, maybe, and then either use the memory button to store that or write it down and then do this division and then multiply it by 1.96. It's much better if you can do this with a scientific. Let me show you how I would do it on a for function in case you have to use one. So first I would do 50 square root. Okay, and then I would put this in the memory using the, where is it? M plus. Yeah, as long as the memory was clear, I would add that to the memory. So now what you can do is you can clear, and if you do MR, memory recall, it puts that number in again for you. Okay, so now I would do 7.1 divided by that number, 7.1 divided by memory recall equals almost 1. And then I'm multiplying that by 1.96 times 1.96 equals, okay, so I got 1.97 if I round to 2 places. All right. So the last step for the confidence interval is I just add and subtract the margin of error from the sample mean. So I'm doing m minus e. That's going to be, sample mean was up here, 110. So 110 minus 1.97. This is rounded to integers, and this is rounded to 2 decimal places. I need to kind of pick somewhere in between those two, I guess, to round to. So 110 minus 1.97. Let's just round that to 108.0, I guess. All right, and then m plus e is going to be 110 plus 1.97. So, I can do that one myself, 111.97. If I round that, it's going to round to 112 exactly. So the 7 rounds the 9 to a 0, which means I carry over and increase this digit as well. So this is going to round to 112.0. Okay, so now what do we tell the CEO of this company? So this is the interpretation statement here. We can have whatever percent confidence. It told us to do 95%, so we can have 95% confidence. That's one way to phrase it, or you can phrase it as there's a 95% probability that the population mean, the mean caffeine level, is between the 2 numbers we found. Okay, so I'm going to write that here. Maybe I'll just do it here. There is a 95% probability that the mean caffeine level, meaning in the whole production line, is between 108.0 and 112.0. So this is what you would tell the CEO of the company. So if you wanted it to be like dot on 110 or dot on like 111 or something, it's not clear that that's the case, but at least it's very likely that it's between these 2 numbers. All right, so that's the end of, oh wait, I'm sorry, we forgot to circle back to this random sample thing. So I think we would have to tell the CEO this as well. Maybe we put it at the beginning of the sentence to emphasize how important it is. As long as the sample was collected randomly, then there is a 95% probability. But if it wasn't collected randomly, we really can't say anything. This might be a really biased estimate if it wasn't collected randomly. And I mean biased in the numerical sense, where you're shooting away from the real target that you're trying to hit. Okay, so that is the end of that part. Let's go ahead and we're going to do a couple more of these, and then we have some more kind of thinkier ones at the end. All right, so for the paper, a critical appraisal of 98.6 degrees Fahrenheit, researchers at the University of Maryland conducted a study of 148 healthy men and women's temperatures. The mean oral temperature in their study was 98.2 degrees Fahrenheit. Assuming the standard deviation is 0.63 degrees Fahrenheit, we're going to do these 3 things here. All right. So first we need to check the 3 assumptions for the procedure, and they're written back up here. If you forgot them, I have them memorized, so I'm just going to go off my own memory down here. So was this a random sample? Actually, again, I really can't tell. It doesn't say it was random. I mean, then that really matters. I mean, it matters how you collected these people. Like if it was 148 college students, then you haven't got like a good unbiased estimate of everyone's temperature. You've got an estimate of college students' temperatures, right? And I mentioned college students because they're like popular participants in studies, because professors can sort of get them to do things more easily than other people. if it was a sample of 148 people they found standing outside on a cold day, then that would also be biased. So it's kind of unclear where they got these people. But this is not clear. So we need to mention this in the interpretation. Okay. Now, the second assumption is, oh, I did forget. That we know the population standard deviation, right? Well, it's not clear if we actually know it, but we're going to go ahead and assume, it's told to assume that it's this, and so we're going to go off of that assumption. Told to assume. So if that actually turns out to be wrong, then of course that also means our interpretation would not be correct. Okay. And then lastly, either the original data has to be normally distributed, or we have to have a large sample, or kind of something in between. This is a very large sample. 148 is quite large. So definitely, if you're taking many random samples of that size, they will be normally distributed for sure. Okay, very large sample. 148. Okay, so now we're going to follow the steps. So the first step is calculate alpha, which is 1 minus the confidence level. And the confidence level needs to be expressed in decimal form, because we're doing 1 minus to get the opposite probability. Okay, so we're doing 1 minus 0.9, so that's 0.1. That's going to be the total tail area in our sample mean distribution. So we need to split it into left tail and right tail, so we're dividing this in half. So that's going to be 0.05. And then we are finding z sub 0.05, so that is the z-score that would cut off the right tail of 5%, and then the negative version will cut off the left tail with 5% area. So that tells you where the z-scores are that isolate the center 90% of the sample means. Okay, so you'll either have a list of these, or you can look it up in your table. So we want to do a reverse lookup. You can either look for the z with this much area to its left and then make it positive, or you can look at the z with the opposite area to its left. So the meaning of the z with the subscript is this is z with 0.05 area to its right. So that means that it will have 0.95 area to its left. Okay. So if we do a reverse lookup on 0.95, let's see what we get. 0.95, boop, 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 it's between these two. So between 1.64 and 1.65, I don't care which of those you use, just pick one, or you can go halfway between them, that's fine too. I'll just use the smaller one, I guess, 1.64. Okay. Right, and I did get the positive version of the z-score by looking for the, by taking the opposite area and then looking for the z with that on its left. The other way you could have done this is if you just looked up 0.05 in this table. Yeah, it's between these two. So this would be negative 1.6, either 4 or 5 again, and then you would just take the positive version of that z-score. Okay, so now we're going to calculate the margin of error, and the formula is up here, so I'm just going to copy it from up here. So it's our z alpha over 2, which we just looked up is 1.64, and then we're multiplying that by sigma, the standard deviation, which is boop, 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 boop. We were told to use 0.63. Okay, and then on the bottom, the square root of the sample size, 48. Okay. I'm going to do it again and show you how to do it on a 4 function, just because that's like the hardest possible option. If you have a scientific calculator, it's just plug it all in with parentheses in the right places. So now I have a memory that I saved from before from this number, so I'm going to clear that. You can use MC button, or if you don't have an MC button, let's say I put 8 in the memory using M+. I can then, if I want to clear it and I don't have an MC button, we just hit C again. Memory recall, there's my 8, and now do M- to subtract that from the memory, and now you've got 0 in your memory, so it's basically reset at that point. See if I do MR now. Yeah, 0. Okay, so I'm going to do square root of 148, and we'll put that in the memory. I mean, you can write it down if you want to, just you'll have to round it if you want to use your paper as a memory instead of the calculator. Okay, m plus to put that in the memory. Okay, now I'm going to clear 0.63, divide by the number I just got for the square root, so mr to retrieve it. Okay, enter. And now I'm going to multiply by 1.64. Okay, I'm getting 0.08. Let's round that to 0.085. So 2 significant digits. I keep forgetting to use the little approximation symbol here when I round. All right, so that's our margin of error. Margin of error should always come out positive. If it came out negative, you probably just looked up the negative z-score, so you can just switch it to the positive one. Anyway, you're going to be adding and subtracting it, so as long as you end up getting the version where you added it to m and the version where you subtracted it from m, it's fine. Okay, so little m here is our sample mean, which was 98.2. So 98.2, and now I'm going to subtract the margin of error, 0.085. Okay. So clear 98.2 minus 0.085. 98. Let's just round that to one place, I guess 98.1. All right, and the other side of the interval is at the upper end of the interval is at 98.2 plus 0.085. Okay, 98.2, 98.3, let's round it up. Okay, so our interval goes from 98.1 to 98.3. Now we interpret the meaning of this interval. So I need to circle back and check and mention any assumptions that were not fulfilled. So the random sample was really not clear. So I'm going to make a note about that. As long as the sample was randomly collected, there is a 90% probability that the real population mean is between 98.1 and 98.3. So apparently not 98.6. We've all been told 98.6. Guess not. It's probably between these two numbers. As long as they collected that sample randomly. But I don't know if they did or not. Maybe they rounded up a bunch of people that were freezing cold. Who knows? I mean, they did at least say that they were healthy. So like, yeah, it would only, the population mean we get would only apply to healthy people. That, I presume, is because they didn't want to include people that were feverish or like having, what's it called, when your temperature gets too low, hypothermia. Okay, let's quiet the ADHD brain and move on to the third question here. An experiment is conducted to examine the susceptibility of a certain kind of lemon tree to a specific insect larva. I guess by susceptibility they mean that the insects are making the tree sick. Yeah, insects do sometimes lay their eggs like in fruit, so then it could infect the tree, I guess. Maybe? I don't know. Okay, anyway. Oh no, you know what? I shouldn't go on about bug facts at length, but I just remember that bugs can also like get under the bark and eat the sort of soft inner wood of the tree and make them sick that way too. Okay, we're all bug nerds here, right? All right, 40 of the trees are selected at random. Good, we finally got at random. And subjected to the larvae and examined after a certain amount of time has passed. Ah, they told us right here what it is that the bugs are doing. They're eating the roots of the tree. Okay, the number of larvae per gram on the roots of the tree are then counted. And for the 40 trees, the mean number of larvae is 9.02. Would you guys like to have this job where you go out and dig up tree roots and check how many bug larvae are on them? Sounds kind of fun to me. Okay. So we get the mean number of larvae, that's the sample mean for those 40 trees. And then we're given an assumption that the standard deviation is this, although they don't really justify that, but okay. So we're going to check our 3 assumptions as usual. So fortunately, this time around, it is a random sample. We're told to assume sigma is 1.12, and we do have a large sample size of 40. Okay, so we follow our 5 steps here. So alpha is 1 minus the confidence level, which is given right here as 99%. So I'm doing 1 minus 0.99. Oops, that's 0.01. And now I'm going to cut that in half to split it into 2 symmetrical tails. So alpha over 2 is going to be like 0.5%, so 0.005. Okay, now I need z sub 0.005. And I'll give you guys these on quizzes and tests, but for now I'm just going to look them up because I don't have the list of them with me. So 0.005, where am I at? Oop, it's between these two, I think. So negative 2.5, 7 or 8. And once again, I did I actually looked up the one that had that area to its left and not to its right. So I need to take that z-score and make it positive. So negative 2.5, I'll just go with the smaller one, 7. I'm going to make it into positive 2.57. Because if I look at positive 2.57 over here, these two, no, this one is for 7, right? Yeah. This would be the one that has 0.0051 area to its right. And so 0.9949 area to its left. Okay. So the z-score should always come out positive on this particular procedure. All right. So for part D here, we're doing margin of error. I'm just going to copy the formula again. Okay. So for z alpha over 2, I'm getting 2.57. And then for the fraction here, sigma goes on the top. I was told to use 1.12, the square root of the sample size on the bottom, which was 40. And maybe just to change it up, I'll do it in a scientific calculator method this time. Let me put this in. Oh, it claims it's in scientific mode. You are not in scientific mode. Don't be silly. Okay, well, I guess it's something in between scientific and for function. It does at least have these parentheses, so I'm going to make use of those to do this all in one fell swoop, which is how I would do it on a scientific. So 2.57 times, and then I'm going to do 1.12 divide by, and now I'm going to put parentheses around the square root part because the way square root works on this calculator is you have to type the number and then hit the square root key. So I'm going to do parentheses 40, and then I hit the square root key right here. Boop, and then close parentheses. Boop. Okay, and then hit enter, and that should give me the right answer. So 0.46. One rule of thumb for checking if you got the right answer here is it should be smaller than your starting standard deviation for the population. It's always a smaller number if you compare them. Like up here it was 0.63, and then the margin of error was this. And original problem here we had standard deviation originally was 7.1, margin of error was 1.97, so it's always smaller. Okay, that way at least you can tell if you made some horrible arithmetic error, though it won't catch all of them. All right, so now we add and subtract that from the sample mean. Sample mean was 9.02. Oh, good, we got the same number of decimal places this time. 6, so we'll keep 2 decimal places then. 6, 8.56. And for m plus e, 9.02 plus 0.46. Oops, I always put a 0 in front of my points because it's hard to see points if you don't put that 0 there. So it's polite to put it. 9.48. Okay, so this is my margin of error. And now I'm going to mention it. I'm going to interpret it. Did I have any caveats up here? No, these were all checked off. Aside from this assumption, but I assume whoever's writing a paper about this information is going to mention why they made that assumption. Okay, so my interpretation then is we can have 99% confidence that the population mean is between 8.56 and 9.48. Okay, that is my interpretation. All right, so the last two parts here are a little more thinky. In this section, assume that the population standard deviation is known and that the sample was selected randomly. Refer to the last section of the April 6 notes, which contains a more detailed way of assessing assumption C from the one mean z-interval procedure to decide whether use of the one mean z-interval procedure is reasonable. Explain your answers. Okay, so I'm just going to open those notes and grab that last section. Okay, so we did not have time to get to this in class, unfortunately, so it's good that it's in the homework video. These are some more information about assumption C. So this whole procedure relies on the idea that the sample means are going to be approximately normally distributed, meaning if we took a histogram of many sample means, it would look like the normal curve. So this procedure only works if that's approximately true. And as you guys might recall from the numerical experiments we did in class using Excel, if the original data has some shape that is highly non-normal, then as you start to take small samples of it, the sample mean distribution sort of shifts away from that original distribution and towards the normal distribution. It sort of morphs from the original shape to the normal shape. So you can be like somewhat in between if your sample size is smallish. So for small samples, say 15 and under, we really only want to use z-interval procedure if the data was approximately normally distributed to begin with. For medium samples, say 15 to 30, z-interval procedure is okay unless there are any outliers, or if you, for some reason, happen to know the data is highly non-normal, outliers is probably a good enough check. And by the way, how do you check for outliers? There are a few different formulas that people use. The way we had done it in this particular class was by making box plots in Excel, and then we could see the outliers on there. They were detected for us as little outlying points. For large samples, say 30 or larger, the z-interval procedure is pretty much fine as long as there are no extreme outliers. Yeah, so even when you've got a large sample size, I mean, you could still have, super non-normal data. These guidelines they're somewhat flexible, they're subject to interpretation, and the normal distribution itself is this kind of theoretical object that never exists perfectly in real life anyway. It's just an approximation, because all real data is discrete and not continuous. But you should keep these in mind anyway. These are the sort of theoretical underpinnings that we're getting at. We're getting under the car and we're kicking the theoretical tires to see if they're going to hold up our car, I guess. All right, so I'm going to paste these into the homework, and let's go off of these to answer these questions. So this is the info from the notes. Okay, so for number 10, the data is very close to being normally distributed and the sample size is 10. As long as your data is very close to being normally distributed, any sample size is fine. All of the sample means will be between your original distribution and the normal distribution, so they should be distributed normally. So I'm just going to explain that. Any distribution sample means will have a shape between the original data's distribution shape and the normal shape. So if the original shape was normal, then any size sample means will be distributed normally. Okay, the data is not normally distributed and the sample size is 75. This should be fine. This is really large. It's way larger than 30. So even extreme outliers, I don't think I would be worried about them at this point. This is very large sample size, so any original distribution of the data is fine. Okay, now we have a sort of medium case. The data contains outliers and the sample size is 20. So we're in the medium one here. If the data has outliers, that's pretty abnormal. Normal distribution doesn't have outliers, so we should not use this procedure. So since there are outliers, we should not use the procedure. Okay, so those are my answers. Now let's do the last part. Suppose we want to estimate the mean GPA of all SU students. So this is what we did in the Excel, one of our Excel experiments. Using a confidence level of 90%, which would produce a narrower confidence interval, a sample of 20 students or a sample of 50 students. So what I mean by narrower is like the distance between the two numbers that make the confidence interval. Like when we're talking about the population mean being between two numbers, that's an interval that starts at the first number and goes to the second number. So like this interval up here for the last, what was it for? Oh, the larva on the lemon trees. This is a width of about 1 between those two numbers. Okay, so what would produce a narrower interval? A sample of 20 students or a sample of 50 students? So just use your own like common sense. Which sample size do you think would give you more accurate estimate of the mean GPA? 50 students, right? So yeah, like using common sense, that should produce a narrower interval. We should be able to narrow down our answer using a larger sample size to get a more accurate answer. But we can also drill into the math and look at why that is from a mathematical perspective. So the width of the confidence interval is 2 times the margin of error, because we go from the sample mean down by the margin of error, and then we go from the sample mean up by the margin of error. So it's really this margin of error formula that controls the width. And if we look at this formula, okay, so width of the interval is 2 times the margin of error, which has this formula. Okay, so what can make this bigger or smaller? So where is sample size? Sample size is down here. So if I put a larger number in the bottom, is that going to make this larger overall? Or is it going to make it smaller overall? If I increase the size of what I'm dividing by, doesn't that make a number smaller? Yeah. Okay, so dividing by a bigger number makes E smaller. So the margin is narrower. Yeah, so larger sample size means narrower interval. Okay, and I hope it also makes sense from the fact that the larger your sample size is, the better of an estimate you can get. Let's look at the last one here. Using a sample size of 50, so we're fixing the sample size, which would produce a narrower confidence interval, a confidence level of 90% or a confidence level of 99%. So you might be thinking, well, let me apply the same kind of common sense, and the higher the confidence is, the more certain I should be, so shouldn't that be a narrower estimate? If I have a narrow estimate, I must be more certain, right? Well, actually not really. So if you think about the idea of shooting at a target, like with a shotgun, or taking a bunch of shots with an arrow or whatever, bow and arrow, I guess, which is going to give you more confidence? A shotgun that shoots just dead center? Well, it wouldn't be a shotgun, I guess. A bow and arrow that just shoots dead center, or a shotgun that can cover the entire target? Aren't you more likely to hit if you cover the entire target? Yeah, you are. So actually, if you want higher confidence, you have to make your interval larger. And that's so that you can be more sure by having a larger interval that the right number is actually in there. So the wider of an interval you make, the more sure you can be that the real answer is in there somewhere. It's a little bit annoying, actually, because there's this trade-off between the width of the interval and the confidence level. Sometimes when the intervals are really wide, people feel like it's less useful, but it is what it is, you know? So we can also explain it by looking at this formula again for the margin of error. Okay, so how does the confidence level affect this formula? All right, let's look at this. So where is the confidence level in here? Oop. Okay, that was my alarm to go to class in a minute. Sorry about that. So the confidence level is in here as this subscript, so it affects the z-score here. So the larger the confidence is, remember the first thing you do to calculate alpha is you subtract the confidence from 1, so that means the alpha is smaller. So the smaller alpha is. And if alpha is smaller, where does that put the z value? So this is the z value with alpha over 2 area to its right. So if I want a smaller area to the right, I have to push the z-score further and further away, down, going towards the right. The smaller alpha is, and the larger z sub alpha over 2 is. Okay, so larger confidence makes E larger. Okay, makes your interval wider. All right, that's it for this homework. I hope you understood it. If you didn't understand it, come to office hours, and I will see you in class.